Hey, hi guys. Welcome back to 360DigiTMG's domain analytics program. And yeah, I hope everybody is doing great. So yeah, without wasting time, let's get into the session, guys. Yeah, it is the seventh day of domain analytics. Till now, what are the topics we have discussed? I'll be going through briefly, and then we'll get into the today's session. So, since if you are following this domain analytics, in that case, you might be having an idea what domain analytics we are talking about. We are discussing about the banking and the insurance analytics. So, what are the applications we'll be having of machine learning and AI when it comes to the banking and insurance analytics? How it will be helpful. So these things we are discussing, and we have taken the various use case scenarios and how we can apply those algorithms, machine learning algorithms, when it comes to real time use cases. So we have discussed a few use case scenarios as well. So today we will be discussing about the simple linear regression. If you haven't have an idea regarding what topics we have considered, gone through till now, let me briefly go through it. We have discussed applications, and we have discussed crisp MLQ methodology the first day, and second day we have crisp DM. First, previously we used to call it as a crisp DM. Now it is converted to crisp MLQ. Crisp DM means cross-industry standard process data mining. So in that we don't have that last phase monitoring and maintenance. Monitoring and maintenance we don't have previously, and then when it comes to crisp MLQ, we have added that monitoring and maintenance. So now new new methodology will be having crisp MLQ, machine learning and quality assurance. So this, what are the phases we'll be having when it comes to crisp MLQ? So what we will be doing in each and every phase. So in detail we have gone through on the second day, and then on third day we have discussed what are the supervised and what are unsupervised algorithms. What are the difference between these? So when it comes to supervised, how we will be training the machine learning model, and when it comes to unsupervised, in that case, how we will be training the model, and what is the hierarchy, what is the process, chronology. So we have discussed when it comes to third day, and fourth day we have discussed about unsupervised. One of the unsupervised, most frequently used unsupervised learning, that is K-means. K-means algorithm. So what exactly the K-means is, and what is the mathematics behind that K-means, and how it will be useful. How we will be how this K-means will be useful to do the segregation, classification or grouping of data. So that we have discussed on the fourth day, and fifth day we have gone through supervised algorithms. So unsupervised we have covered only K-means, and when it comes to supervised, very first algorithm we have discussed KNN, K nearest neighbor. So what is the K nearest neighbor and how it will be helping us to do the classification? So what is the mathematics behind it? We have discussed that, but we have used KNN regression. We will be using the KNN for both. We can use both for the regression and classification, and we have used KNN regressor in order to do the prediction of prices. And sixth day, in the last session, we have discussed about the decision tree algorithm. So what exactly the decision tree and where we will be using the decision tree and how it is doing the classification, what is the working principle behind the decision tree. So and all these things we have discussed in the decision tree algorithm. In the last session we have discussed and we have taken one use case scenario as well. So these are the concepts that we have discussed till now. And today we'll be going with one of the supervised algorithm, that is simple linear regression. Yeah, here you can see simple linear regression. So we have already seen, right, what exactly the classification and what is the regression. So what is the difference between these two? When it comes to in supervised only, we'll be using both classification and regression. When we will be going with the classification, if you have a label data, that label data, that is output, or you can say output data, if it is discrete or categorical, in that case we will be going with classification. In that case we will be going with classification. If it is continuous, that label data is continuous, in that case we will be going with regression. Classification and regression, these are the differences we'll be having in between the classification, when we will be going with classification, when we will be going with regression. So we will be discussing in supervised algorithm only when you have output, or when your output is continuous data, in that case we'll be going with regression. So we'll see what is the mathematics behind it, how this regression will be working. So what are the things that we have to keep in mind? What are the assumptions we'll be having when we are going with the regression? So all these things we'll try to understand in this class. Yeah, we'll go through what is the agenda, regression analysis. So what exactly the regression is? What is the linear model? So what exactly the linear model is? And what is the correlation analysis? How it will be helping us to build a better model or come up with a good accuracy, and equation of the straight line, and how it is similar to the regression, simple linear regression, and what is the difference between multiple linear regression and simple linear regression also we will see, and what are the assumptions we'll be having when it comes to simple linear regression and multiple linear regression. We'll go through those, and then we will be having one use case scenario. We'll try to apply in real time, and we'll see how much accuracy we'll be getting, how we will be tuning the model. All those things we'll try to understand in this class. So yeah, without wasting time, we'll get into the regression analysis. Regression is used to study the relation between the two variables. So scatter plot, you might be having an idea. Yeah. Regression is used to study the relation between the two variables. We can use simple linear regression if both dependent variable and independent variable are numerical. So when we will be using the regression, both output should be continuous or numerical, you can say. Input also should be numerical. If it is not, in that case, we have to convert whatever the categorical data we have into numerical. If the dependent variables is numerical and the independent variables is categorical, it is best to use ANOVA. It is one of the ANOVA technique to convert whatever the categorical data will be having into the numerical one. The following are the situation where we can go with regression. Let's say, So when we will be going with regression, what kind of assumptions we need to have? So you can see at the very first example, testing if IQ affects income. Do you think IQ will affect the income? Obviously, when you have more IQ, in that case, you can fetch good salary, right? Good job. If we are fetching good job, in that case, we'll be getting good salary. So IQ definitely affects the income. So here IQ is an independent variable, but income is dependent on that IQ. IQ is an independent variable. It is not depending on anything, but the income is depending on IQ. And here testing if hours of work affects the hours of sleep. So if you work more number of work, in that case, do you think it will affect the sleep? Dependent variable is hours of sleep here, and hours of sleep. Sorry, dependent variable is hours of sleep, and the hours of work is independent variable. So in that case, if you work more, in that case, you will sleep more. And the performance is also, if you have a good sleep, in that case also the performance of the particular person will be more. If you don't have a rest, proper rest, in that case you won't be able to perform better, right? So it is also dependent. What is the performance of the one particular person will be depending on this. So it is a dependent and it is a independent. Similar to that, testing if the number of cigarettes smoked affects the blood pressure. Number of cigarettes smoked is an independent variable and the blood pressure is a dependent variable. When you go with multiple cigarettes, number of cigarettes you are increasing, in that case definitely there is a chance of being getting the blood pressure, high blood pressure. So these are what all inputs, independent and dependent variables. So if you plot these on XY plane, if you plot these on XY plane, in that case you will be getting the relationship. So IQ, let's say I have taken the IQ on X-axis and the salary on Y-axis. Salary and IQ. IQ is keep increasing. In that case, salary is also increases. So let's say IQ is this. In that case, salary will be similar to that. Only will be having. If IQ is increasing, in that case, salary is also increasing. IQ is increasing, salary also increasing. So like that, you will be having. So what kind of relationship we have here? Positive relationship we have. As X is increasing, in that case, Y is also increasing. In that case, we will be calling it as positive relation we have. So here, to represent that particular relationship, we have scatter plot. So what exactly the scatter plot is, we'll try to understand here. It is important to perform a scatter plot because it helps us to see if the relation is linear or not. So whatever the two components, variables that we are taking, what kind of relationship we have first? We have to understand first that, and based on that, we will be going with regression analysis. So to find out the relation between the two numerical data, or you can say continuous data, to find out the relation between the two continuous data, in that case, we will be using the scatter plot. We will be using scatter plot. So you can see here, IQ is increasing. IQ is increasing, in that case, salary is also increases. So if you have a 60 IQ, in that case, you have a salary in that range only. If you have IQ of 80, 90, in that case, you have a salary of in that range only. If you have an IQ of 120, in that case, you have a salary range in that particular range only. It is increasing. So what kind of relationship we have here? Linear. linear relationship will be having. When both the dependent variable and the independent variable are numerical, we can represent data in the form of the scatter plot. If both are numerical, in that case, we can be able to represent. If you have categorical data, in that case, we won't be able to represent something like this. So it is a linear relationship. So is it always you will be having the linear relationship? No. It is not always, you won't be having always a linear relationship. And sometimes you will be having non-linear relationship as well. You can see here, it is a plot in between body fat as well as the, what is the risk associated with that particular body fat and cardiovascular diseases, or you can simply say chance of heart failure. So when you have most fat, if you have a fat, in that case, it will definitely affect heart health. So how it will change when you have, how it will be affected when you have different fats, we'll try to understand. So if we have a body fat percentage and the chance of heart failure. So these are on x-axis, we have taken the body fat percentages and chance of. So if you have less fat, when you have less fat, so you might have come across so many, news. You might have come across news, right? Person who was doing gym suddenly collapsed and his heart stopped working. Some this kind of news, very frequently you will be getting. So what exactly that means? That means, does he have fat? Even though you have a lean body, if your fat percentage is less than 5%, less than 2%, or even 1%, in that case also, we will be having risk of heart failure. So we have to balance that body fat ratio. The body fat ratio should be some, we need to maintain some amount of fat in order to live a healthy life. Even though if you have a less body fat, in that case also it will lead to the heart failure. If you have a more body fat, in that case also it will lead to the heart failure or having the cardiovascular diseases like related to the heart diseases. So you can see this represents linear, not linear. It is not a linear. It is a curvilinear. So even though you have body fat, less body fat, and see here, it is a less body fat and the high body fat. For both, the risk is more. So you have to maintain thin. You need to maintain some body fat in order to live healthy life. So these are the, it is not a linear, it is a non-linear distribution we have. That the relation between the body fat and chances of heart failure. So how we will be finding out the that relation? How and what are the various relationship we'll be having when you have a scatter plot? What things we can able to understand? What are the things that we can infer? So that we'll try to understand. First thing, we'll be understanding the relationship. What kind of relationship we have in between those two features. And second is how strong it is. How strong that relationship is. So we'll try to understand that. So you can see scatter diagram provides a plot provides a graphical representation of two continuous variables. We must be careful that correlation. Yeah, well, there is one more thing we need to discuss. Correlation. So these are all correlation. Correlation doesn't mean causation. Causation means cause and effect relationship will be having, right? Cause and effect. So it is not always the same case. So here we have taken the IQ and salary. It might be the cause and effect relationship, but always whatever the cases we are taking, it is not cause and effect relationship only. Even though you don't have any cause and effect relationship, still it can have this good correlation. So it is not always the case, but it is also part of it. So cancer, let's say cancer. Do you think only smoking can cause the cancer? No, it is one of the cause, but it is not the only cause. So cause and effect relations can be plotted using the scatter plot, but it is not the always case. Even though we don't have any cause and effect relationship, we can we can have the good correlation in between the two variables. So that is one more thing we have to keep in mind. So you can see here, I'm taking X and the Y. X axis and Y axis, and I'm plotting my data points. When you plot these data points, you can see here, and if you draw one line, so all the data points are along that line, the regression line. So if all the data points are on that line, in that case, we'll be calling it as strong relation. And it is X is increasing, and in that case, Y is also increasing. In that case, we'll call it as positive correlation. Positive and strong correlation. It is a positive and strong correlation. And here you can see it is X axis and it is Y axis. So if you draw a line here, not all the data points are present on that particular line. Of course, it is a positive relationship. X is increasing and Y is also increasing. But these points are on that particular line, just single line? Most of the data points are present on the line? No. So it is a positive correlation, but moderate. It is not that strong as it is. So it is a moderate positive correlation. And then we have no correlation. What, irrespective of what X value we have, there is no change when it comes to Y value, irrespective of X values, whatever the X values will be having. And the first two cases you can see here, when you are increasing the X values, in that case, Y values are also increasing. But when it comes to this, no, while even though X values, irrespective of X values, Y are also, these are independent of each other. So in that case, we can say there is no correlation. There is no correlation. Similar to that, here you can see if X is increasing and Y is decreasing. So in that case, we'll be calling it as negative correlation. It is moderate negative correlation. If it is all the data points are on that particular axis or line, in that case, we'll be calling it as strong, but all the data points are not on that, so we will be calling it as moderate negative correlation, since it is decreasing. And here, strong negative correlation, if all the data points are on that line, most of the, not all, most of the data points are on that line, in that case, we'll be calling it as strong negative correlation. So here we'll be having, it is not always we'll be having the linear, it is a linear, it is also linear, it is also linear. It is not always you'll be having the linear correlation. You will be having non-linear as well. You can see here, first it is decreasing and then it is increasing. In that case, we'll be calling it as curvilinear. Curvilinear relationship. So, judging the strength of the relation by width and tightness of the scatter plot, just by using the scatter plot only, we are judging, but it is subjective. It is a subjective. I might say that it is a strong. You might say it is just a moderate relationship, moderate positive relationship. So it is always subjective. I might be thinking it is strong. You might be thinking it is moderate. In that case, to avoid that, we will be going with correlation coefficient. So whatever the correlation we have, we are quantifying that. Quantifying means we are simply converting into correlation coefficient. So here we will be having the curvilinear. It is not always we will be having the positive or positive correlation and negative correlation. Always you won't be having the linear. You can have the non-linear as well. So these are all subjective. So when you have a subjective, in that case, you won't be able to understand clearly. It is strong relations or moderate relation. To quantify that, whatever the correlation will be having, in order to quantify that, we will be using the correlation coefficient. So what we will be doing, whatever the correlation will be having, we are getting in numerical value. In numerical value. So this is regression, how we will be finding out the correlation between the data. Okay. So linear regression model. So how the linear regression works? What is the mathematics behind it? What is the main equation behind the linear regression? We'll try to understand. So here we'll be having one linear equation line is. It is similar to y is equal to mx plus c. Y is equal to mx plus c. So here what is m? We'll be having the slope, and it is a constant value we'll be having, and it is the axis that you are talking about. Here we are similar to this. We'll be having y. It is an output. The predicted output will be having, and b. It is a coefficient. Coefficient of whatever the linear. Input that you are using. X is the input, and then we have a constant, and then it is an error term. It is an error term. Just a minute. So the linear model. In regression, the relationship between the y and x model in the following form. So similar to the line equation we'll be having, right? Similar to that only we'll be having the regression equation. So here y is an output like we have discussed, and a is a constant value, and b is a coefficient of with respect to that particular input feature, and then we'll be having error term. So that description only we have given here. Y is a dependent variable that is dependent on input features. Based on the input features only, we will be doing the prediction, right? Like we have discussed, IQ and income. IQ definitely impact the income. Definitely it will impact, right? As IQ is increasing, in that case, income is also increases. So here we are considering IQ as the input variable that is independent. It is not dependent on anything. But when it comes to income, is definitely depends on the IQ. So here it is x is an independent variable and here y is the dependent variable we'll be having, and a is an intercept, that is we'll be calling it as constant as well, and b is a coefficient of what? Input feature. Let's say IQ. For that we will be having a coefficient, that input value coefficient will be having, and e is an error term for each observation. So what exactly when you are doing some prediction based on historical data only, we will be doing the prediction, right? So input and we have an output. So we will be having the real actual values also will be having for that, and we'll be comparing those actual values and the predicted values. Whatever the difference we will be having, that we will be considering as an error term for each observation, since there is a additional variation not explained by the income. So that is actual minus the predicted one. So that difference will be given by error term. So the error E are normally distribution. So the assumptions we will be having when it comes to linear regression, this error term we will be having, right? It should be normally distributed. The error term should be error value. The errors should be normally distributed. This is the assumption we'll be having when it comes to linear regression. This can be tested by plotting the histogram. You can simply go with the histogram. In that case, we can easily able to understand whether it is having the normal distribution or not. Histogram of the residuals of the regression and checking that they are all part of the bell-shaped curve. So whatever the error term we will be having, whether we are having in the bell-shaped curve or the normal distribution or not, we can able to check using the histogram. So this is the linear model, and what are the components we will be having when it comes to linear model. So correlation analysis measures the degree of linear relationship between the two variables. The correlation itself, what is it? That is the relation between the two variables. The range of correlation coefficient x in between -1 to +1. So here, if we have -1, in that case, absolute negative values will be having. And when it comes to positive, good correlation or perfect positive correlation, we can call perfect negative correlation we can call. So if it is 1 + 1, in that case, perfect positive correlation will be calling, and comes to negative, in that case, we'll be calling it as perfect negative correlation. So you can see here, this on x we have some, and y we have one more variable, that is should be numerical, right? So when you draw one regression line here, do you think the data points are on that? So yeah, as x is increasing, the y is also increasing, that is fine, but is it having all the data points on that particular line only? No. So here, what kind of correlation will be having, guys? Poor correlation will be having, that is 0.4. We have a correlation, but it is not that good of correlation. It is not a strong correlation. So here we can see on the plot, this plot, x values and y values. Irrespective of these x values, y values we will be having. So it doesn't matter what x value you will be having. Y values are randomly distributed. So even though if you draw one regression line, do you think it is following some pattern? No. So here we can say we don't have any correlation. And here we'll be having negative. So if x is decreasing, in that case, y value is also decreasing. In that case, we'll be calling it as negative correlation. Is that strong? No, it is 0.4. Moderate or less correlation will be having. So these values, how we are finding out these values are, it is a correlation coefficient. It is a correlation coefficient. So in order to find out the correlation coefficient, this is the formula. R is a correlation coefficient. That is quantifying, right? Whatever the correlation we will be having, we are simply quantifying. So in that case, we'll be using the R. So you can see x and y, these are the features that we are considering, or the variables that you are considering. Sigma of x and y minus summation of x into summation of y, that is also summation, and this is the formula in order to get it. So we don't need to remember this whole formula. So we just need to know because we won't be using any manual calculation when we are doing the finding out the correlation. We'll be importing the library, respected library, and then we'll be calculating just to have an idea how the correlation will be calculated. For that, we have given this formula. Ordinary least square. So it is the error, or you can say evaluation, kind of evaluation, which regression line I have to consider. So we have seen, right, the regression line, how we can come up with that particular regression line based on what. So for that, we will be having the ordinary least square. So what exactly the ordinary least square is? OLS techniques also we can call ordinary least square. Is a common technique for estimating the coefficients of linear regression equation which describes the relation between the one or more independent quantitative variables and dependent variables. So here we are having just one input, simple linear regression, that is X. Output, it is a Y. So I am simply using the inputs and outputs. On x-axis, I'll be taking X input, and y-axis, I'll be taking the output. So these are the mixture of two variables, two continuous variables, X and Y. What I will be doing, how can I come up with the regression line? This is the regression line. Directly, we are not going with this. We will be doing the multiple iteration. Let's say first I have done the regression line this. And then one more regression line I have used like this. One more, and one more regression line, one more regression line. Various regression lines we will be drawing. But how can we come up with this one final regression line, guys? Based on the error term. If the error term is the least, in that case, that is the best regression line. That prediction, regression line means prediction. That is what you are doing, the prediction, right? So these are the actual values and these are the predicted values. So like that, we will be doing the multiple iterations of regression lines. First, let's say this is our regression line. This is the predicted one. And these are the actual values, right? In that case, in order to find out the error term, what we have to do? Actual values minus predicted one. It will result in the error, right? So we will be finding out this is a predicted one. The difference will be calling it as error. This difference we will be calling it as error. So how much error we have? Large amount of error we will be having, right? So here the summation of those values, sum of the errors are too much. So I won't be consider this as the best regression line. Again, I'll be doing one more iteration for it. For this, I'll be doing the one more regression line. It is the one more regression line, same actual values, and it is a predicted value. The difference will be finding out. Some of those difference will be taking. That is the RMSE value we'll be having. So RMSE, what exactly the RMSE will be seeing in a minute. So that difference we will be calling it as error. So wherever you have a least error, that is your best regression line. So among these, which one will be resulting the least error? Like that, we'll be calculating each and every error value, whichever giving the least error, that I'll be considering as best regression line. Among these, this regression line will be resulting the least error. So I am considering that as a best regression line. So this is our regression line. So you can see here y is equal to y cap, that is a predicted value. Beta naught, it is a constant, plus beta 1 is a coefficient, and 2x. Those are the input values we'll be having. So beta naught, that is a slope. Beta 1, it is a slope. So these slope values will be getting, and coefficient also will be getting. Y-intercept it is, and it is a coefficient. So it is a constant. Y-intercept wherever it is striking that y-axis. In that case, we'll be calling it as y-intercept. So here beta naught is a y-intercept, and this one is your coefficient. So using this, we will be predicting the x-axis. So let's say we have taken the IQ as an input. In that case, y is equal to beta naught plus beta 1 into IQ. So that will result in the output, that is the prediction. So for those IQ values, we'll be finding the slope that beta 1 will be capturing here, and the constant will be having it. Those will be capturing. If you substitute all these values in that case, respected IQ values, and what will be the salary. So that is we will be getting when it comes to regression. So that is a OLS techniques. OLS techniques, why we are using OLS technique to decide which regression line we have to go with. So whatever the regression model that you are building, how can I say that it is having a good model? And based on what? What are the evaluation metrics will be having? So to tell whatever the model that you are building is a good model, we have R square value. We have one thing called R square value. It is a coefficient of determination. What exactly the R square value is? It represents percentage of variation, whatever the variation that is happening in output, that is dependent variable explained by the independent variable. That is, so whatever the variation that you are doing when it comes to input variable, so how much that change, the variation is captured by the output. So that value only we will be calculating. It represents percentage of variation in the output, dependent variable explained by input variable or percentage of response variable variation that is explained by its relationship with one or more predictors. It is not just for the one. So even though you have multiple inputs, so here we have just one input, IQ and salary. IQ is independent and salary is dependent. Like that, if we have multiple x1, x2, these are all predictors, you can say inputs, and then I have y output. Even though you have a multiple inputs, if you are doing some variation, if you are doing some changes, how much it is resulting in the output. So that we will be able to capture that variation we can able to capture by R2 value. R square value will also called as coefficient of determination. In that case, how much value it should be? How much value it should have in that case will be calling it as good. How much value it should be having in that case, we can say it is a medium or low, something like that. How can we come up with that? So you can see higher the R square value, the better the model fits your data. The more the R square value in that case, better your model is. R square is always in between the 0 to 100. So we will be representing the R square value into the 0 to 100. This kind of accuracy you can say. For that, we will be having some conditions. First, we will be looking into some p values. In that case, we will be looking at those R square values. If all are in the limit, and in that case, if you have a good R square value, in that case, we'll be considering that value. So R squared is in between 0.65 to 0.8. Normally, we will be considering as 0 to 100, but in percentages, we'll be taking like 0 to 1. R square value you will be getting it 0 to 1 only. So here R square is in between 0.65 to 0.8. In that case, we can call it as moderate correlation. Moderate correlation. If R square value is greater than 0.8, in that case, I'll be calling it as strong. Whatever the model that you are building, it is a good model. So to understand that, we need to have how we will be coming up with the R square value. So from where we are extracting this R square value, to understand that, we need to have SSR value, sum of the squares of regression. So what exactly that is? It is a difference of sum of the difference of predicted values and the mean. So it is a prediction value and it is the mean of those square value we will be getting. Sum of the squares of regression, prediction value and the mean. If you square it and if you sum all the points, in that case, you'll be getting the SSR. Sum of the squares of error. What is error? The difference between the actual values and the prediction value. So that if you find out the sum of those, in that case you will be getting sum of the squares of error. If you combine both, in that case you will be getting sum of the squares of total. So both sum of the squares of regression, sum of the squares of error, it will result measure of total variation in Y. So in order to find out the R-square value, we will be finding out SSR by SST. That is sum of the squares of regression by sum of the squares of total. In that we will be having both SSR as well as SSC. Sum of the squares of error, sum of the squares of regression. So this value result in between 0 to 1. So that we will be calling it as coefficient of determination. So this is how we will be coming up with R-square value. It will be helping us to determine whatever the model that we are building is a good model or not. It will result. Okay. So we have something like simple linear regression, confidence interval, and the prediction interval. So prediction and the confidence interval are two types of confidence intervals used for prediction in the regression and other linear models. Prediction interval represent a range that a single new observation is likely to fall and given specified settings of the predictors. Let's say if you are building one model, regression model, and you said that 85% accuracy will be having. So whatever the prediction that you are doing, you are 85% confident that it will fall whatever the range that you have given. Let's say you have done the forecasting. In that case, 85% show that whatever the range that you are giving, all the predicted values will be fall in that particular range only. In that case, we will be calling it as confidence interval. In that case, we'll be calling it as prediction interval. It represents a range that a single value, a new observation, whatever the predicted observation will be having, is likely to fall given specified settings of the predictors only. The range you will be giving it, it will be falling into that only. Confidence interval of the prediction. It represents a range that the mean response is likely to fall specified settings of it. Here we'll be talking about the mean response. Here we'll be talking about the actual data points. Whatever the prediction that we are doing, it should fall in that particular range only. So it is a confidence interval we'll be having, and then so here we are 95% confidence interval. In that case, 95% you are confident that whatever the new prediction that you are doing, it should fall in that particular range only. And you are not confident about that. Rest 5%, you don't know. It might fall beyond these particular range only. Range also. For that, we'll be calling that confidence intervals or prediction intervals. So the prediction interval is always wider than the corresponding confidence intervals of the added uncertainty involved. So whatever the prediction that you are doing, it is not 100% exact, right? We will be adding some standard deviation and standard error also we will be adding. So that is very different concept we will be having. We'll be discussing when we are discussing the linear regression in detail, multiple linear regression in detail. So when we will be going with the regression. So when you have output as continuous data, in that case, we'll be going with regression. In that case, what kind of input we will be having? What kind of input we should be having? Let's say it is an output. It is a continuous data. It is also continuous data. And it is a Y. Y should be continuous data. If single, X is a single and continuous, in that case, you can directly go with the simple linear regression. Y is continuous and X is single and continuous. You can simply go with the simple linear regression. If Y is continuous here, X is single and discrete. So it is not a continuous data, it is a discrete data or categorical data set. When you have single and discrete data, in that case, we will be converting into the dummy variables. So we have encoding techniques, right? Among these encoding techniques. Encoding techniques, in that dummy variable creation, we will be having dummy variable creation, whatever the categorical data or discrete data will be having will convert into the dummy variable, and then we will be going with simple linear regression. So this is when you will be going with simple linear regression or multiple linear regression. Multiple linear regression, what happens? Similar to that, we'll be having, instead of single and continuous, we'll be having multiple and continuous. What if you don't have a continuous? In that case, same, whatever the discrete data we'll be having, we are simply converting into the dummy variable regression, and then we will be going with multiple linear regression. So we don't have same input should be continuous. If it is not, in that case, we'll be converting into dummy variables, and then we'll be. When you have a simple linear regression, one input will be having. When it comes to multiple linear regression, we have more inputs. Yeah. Error variables. So what are the assumptions we'll be having when it comes to error terms? We'll look into 4 requirements in one. These are the assumptions we'll be having when it comes to error terms. The probability distribution of E error terms, it should be normal. It should be a bell-shaped curve. The mean of E. So every time if you are calculating the mean of the errors, every time if you are calculating the mean of the error, it will be 0. It will result in a 0. The standard deviation of error term is for all values of x in the standard error. I think we have some typing mistake. The set of errors associated with the different values of y are all independent. So whatever the errors that you are getting, it should be all independent. It shouldn't be having any relationship. If it is having a relationship, in that case, it will be holding some correlation. So if it is having any relationship, in that case, it is having some correlation. In that case, whatever the error terms that we will be getting, it should be having all are independent. Values of y are all should be independent. Yeah. So these are the assumptions we will be having when it comes to errors. We'll try to understand one use case scenario and what is the difference when it comes to multiple linear regression and input, or you can say simple linear regression. So when it comes to simple linear regression, what have just one input and output. It should be continuous. So we don't have any issues with that. Just one input, right? It should be having good correlation with the output. In that case, only we can build better model. So we will be checking whether it is having good correlation or not. Fine. But when it comes to multiple linear regression, so since we are going with the multiple linear regression, so what are the factors that we have to consider? Multiple linear regression, multiple inputs we will be having. Those inputs should be continuous or numerical. If it is not, if it is discrete or categorical, in that case, we'll be using the dummy variable creation, and then we'll be converting those categorical data into numerical data, and then we will be doing the prediction. So the thing here, one thing we have to consider here. Yeah. When you have multiple inputs, so multiple inputs we have here. It is one use case that we are doing. Age we have, sex we have, BMI we have, children, smoker, region, and charges will be having. When you have good correlation with output, input correlation with output, in that case, fine. But if you have correlation among these inputs only, if you have a correlation among the inputs only, in that case, it will leads to collinearity. When you have just one input, in that case, you don't have any issues. We can simply go with that particular model. But if we have a good correlation among the inputs variable itself, in that case, it will lead to the collinearity. If you have a collinearity, in that case, it will definitely affect your model. Whatever the accuracy that you are getting, it will definitely affect your model. So in that case, what we have to do first, we have to get rid of this collinearity. So how we will be doing the how we will get rid of this collinearity? Various techniques will be having. Among these, we have one variable inflation factor. So what is the variable inflation factor will be having? So whichever the feature having the good correlation, it will find out the variable inflation factor if it is greater than 10. If the variable inflation factor it is greater than 1, whichever the features having the value it is greater than 10, in that case we will simply drop those features, drop those columns. When you drop those columns, and then again we will be checking the p-value. So if it is in the range, in that case we can simply go ahead with the model. If it is not in the range, in that case again we will be finding out the VIF wherever you are having the high VIF values, we are simply removing it. So like that, we will be getting rid of those collinearity issues. So we'll see this use case and how we can implement that linear regression or multiple linear regression. Since it is having the multiple inputs, so we will be going with multiple linear regression. How we will be implementing that, we'll try to understand. So what is the use case we have here? The insurance data set consisting of this many entries or records, and how many attributes we have? 7 attributes that describe their health and demographic information. So you can see age, sex, BMI, body to mass index ratio, and children, and the smoker, whether that particular person is smoker or not, which region it belongs to. Based on that, we will be predicting the values. Based on that, we will be predicting the values. We have used some common Python libraries in order to analyze the data. We have to import the data. These are the various libraries we have used to come up with the inferences, various inferences. So let's get into it. We'll do some analysis. So if you use head, once the data has been imported into your Python or notebook, if you use head function, in that case you can have a sneak peek the first 5 entries of the data set. You can simply look into it. You can see these are the first, and describe function will be having when we will be using the describe function. So in order to know how the data distribution is done, so count, mean, standard deviation we have, minimum value we have 25 percentage, 25 percentile data, 50 percentile, and 75 percentile. How much data we have in that particular range, and what is the maximum value we'll be having. So age, so what is the minimum value? 18. What is the maximum value? 64 will be having. So when it comes to insurance, we will be considering this age only. If it is less than that, for that we will be using some other insurance policies, and the maximum age we are considering is 64. So if it is more than 64, in that case we won't be considering in general category, and instead of that we will be taking some other insurances. For that the charges vary. If you are young and you don't have any issues, in that case you don't need to change you don't need to pay much premium compared to the people who are aged. If the age is greater than 64, in that case the probability of getting illness will be much higher compared to the young people, right? So that is the reason we will be considering age limit. It is 64, and minimum age we will be taking as 18. So among these, how many number of people we have? Like smokers, how many people we have? Non-smokers, how many people belongs to which region? If you go with unique values, in that case you will be getting this. Sex, count, overall count, how much we have. So we'll be doing the exploratory data analysis, and then claim amount, with respect to the region. So where exactly we have a claim amount more, and do we have any outliers in that, so that you can able to understand using this and distribution analysis, insurance cost and smoking. These all will try to understand. This is a correlation uh, of all the inputs, whatever the inputs we are using, where we have any correlation, good correlation. So output we are taking that the price rate cost. So here you can see a good correlation we have in between smoker and charges. So charges only we'll be taking as the output in that case, no issues. It is good thing we have a good correlation, but if it is having good correlation among the input variables only, in that case, it might lead to the accuracy. It will definitely affect our accuracy. So model building inferences, what are the inferences that we are getting? This is the final regression in between the region. I am considering, instead of combining all the regions, we'll go individual region. Southwest, how good our model is performing, and southeast, how good it is performing. And we have, of course, we have some outliers. So we have to do the pre-processing, and then if you go with the model, in that case, it might result good, because we haven't gone with the outlier treatment and all. So that is the reason you can see these values are very different. So we'll try to understand the same thing using the code, and here. Yeah. So what are we trying to do? The business objective of this simple linear regression. So what exactly we are trying to do, guys? We are simply predicting the charges, premium, how much premium they are supposed to pay. So that I'm trying to predict using the attributes that are 7 attributes should be having, right? Those are the attributes. These are not the only attributes. There are so many other attributes also we can take. But I'm simply considering this for this model. It is a base model, since it is base model. If you want to improve it, in that case, you can improve using various other attributes. So data overview, what are the libraries I'm importing? NumPy, Pandas I'm importing, and Seaborn, as well as Matplotlib for the visualization, Seaborn for the box plot, and Plotly also I'm importing the graph object or the various, I'm not simply dealing with the simple linear regression, I'm using other regression techniques as well to check which one is performing the better. So various techniques are considering, and I've imported the data. You can see the description of the data. So if you know this description, in that case, you will be having an idea whether you should go with the scale, whether we have to convert all these values into single scale, that is normalization or standardization. You will be having an idea regarding that. You see, minimum value, how much we have here? 18 and maximum 64. Here 15 and 53. For that, we don't need to do any standardization. And here you can see 1 and so it is 0, it is a 5, and here 11, 21 to 60,000. So you can see this is a bit too much variance we have. In that case, we can go with the normalization or standardization. Summary, when it comes to categorical columns, how many we have unique values? Sex, we have just 2 unique values, male and female. On total, how many we have? 1338 we'll be having. And when it comes to non-smokers, how many? Total 1338 we'll be having. Among those non-smokers are 1064. And among regions, 364 people belong to Southeast. Among these sex, male people have. So it is kind of balanced data only we'll be having, other than this smoker ratio, non-smoker ratio, we have more compared to the others. Yeah, so how much claims, variable number of, male, how much claims they have done during the, based on historical data, we'll try to bring out some inferences from the data. Male people, how much they claim that they have claimed it is about 40,000. and female it is about 13,000. So not much difference will be having. So male and female we have a balanced data. And when it comes to smoker and non-smoker, so number of policyholders, how many? 1064 are non-smokers and smokers are 274. So average amount claimed by these people. So you can see here 8,000 for the non-smoker people and smokers 32,000. So it is, you can see the people who are smoking in that case, they might be more, they can get illness much easily compared to the people who are not smokers. That is the reason the claim amount for these people are too much. In that case, while we are deciding the premium, when that definitely will increase the premium for smokers because they are the people, smokers, who will be claiming the insurances more frequently. So average huge difference we have at least 4 times. So in that case, obviously, if you keep the same premium as non-smoker people, in that case, company, we need to pay a lot of money back. So instead of that, we can increase the premium amount. So variables and region-wise claims, how much claim amount we have in Southeast average. So how much you have? 14, 12. So it's pretty much same irrespective of which region that particular person is belonging to. It is giving the mostly similar claim we will be having. So distribution of insurance cost by region. So how much they are paying insurance cost by region? How much? I mean, pretty much same we have it. So you can see Southwest how much premium they are paying, about 27,900 something like this. You have here also. It is pretty much same 19,000 we have, and here we have less when it comes to premium cost. Northeast we have way less compared to the Southeast and the Southwest and South Northeast as well. Northwest has the least, that is how much? 29,000. So what are the outliers we'll be having? These are the outliers. If you do the pre-processing, in that case, we can bring back to the normal. So these are the analysis with respect to distribution of insurance cost by smoking status. If you have what kind of smoke, if whether it is smoker or non-smoker, based on that also premium will vary. So these are the inferences that you can get from non-smoker as well as smoker. So these are the various CDS we'll be having here. You can see how average insurance cost by age and smoking. So if you have an age in between the 18 to 29 years, and if you are a smoker, how much insurance cost will be? So 18 to 29, and the people who are non-smoker, we have very less, 4,419 when it comes to this. Okay. When it comes to smoker, you can see 27,000. So vast difference will be having when it comes to non-smoker and non-smoker, and with respect to the age as well. So pretty much, I mean, as age is increasing, in that case, premium amount also increases because susceptibility to get illness, you can easily able to capture when you are growing old. So that is the reason it is keep increasing with respect to age. And absolutely, when it comes to smoker and non-smoker, we have a huge difference. So this is the body mass index. Insurance costs increase with the body mass index. If you have a less body mass index, in that case, how much is the insurance cost, and when you have more, in that case, how much will be have? In that we have used smoker, non-smoker as well. So here you can see less body mass index, in that case less cost. You can see these are all less body mass index. Even though the body mass index in slight increase we have there, just slight increase we have. But if you are a smoker, you can see maximum increase will be having. So less body mass index, in that case we will be having less premium to pay. If it is increasing, in that case it is not having much effect when it comes to body mass index, but smoker is having much more. So these kind of inferences that you'll be getting when you go through these data. And so many other inferences we want to go through. And correlation. What kind of correlation we'll be having? You can see charge and smoker. If it is smoker, in that case, charges for that particular person is way higher compared to any other. So smoking, it is having the good correlation. You can say 0.8. So linear regression I'm importing, and whatever the model that I'm importing, I'm simply passing those linear regression. So with that, I'm passing other as well. So we'll see how the linear regression will result. Southeast, how much R square value you are getting? R square value, we are getting 80, almost 80, and adjusted R score is also 76. And here you can see 90% when it comes to Southwest and 89%, 74 and 71 and 63%, and here is it. So overall, we have good prediction. And when it comes to Northeast, it is not performing that great, but in that case, we can add the features, or you can add the more data, and you can try to increase the accuracy of that particular model. So you can see here, these are the regression lines that we have with respect to various regions. If you want to convert those into dimensions, I mean, dimension reduction techniques, and whatever the inputs will be having, try to convert those inputs into just one or two components, and then also you can able to do it. So model summary, you can see overall how much we got, 74% average accuracy. It is not bad, but there is good scope to increase the accuracy of that particular model. We can add, there are so many other features that is also important, whether that particular person alcoholic or not. If you are alcoholic, in that case, premium charge for that particular person also increases. It is also one of the important features, right? Like that, we have various features that we need to be considered, but overall, it is not that that bad. So if you want to increase that, in that case, you can increase. So this is all about the linear regression. It is not just simple linear regression, guys. It is a multiple linear regression. Overall, this is how linear regression will work, and how we are doing the prediction of the charge. How much charge we have to give based on the inputs. We will be building this model, and we'll deploy it. And when the customer comes to you saying that I need to take insurance, in that case, will be input in whatever the inputs we have built a model, same inputs will be giving. Based on that, we will be deciding how much premium we are supposed to charge to that particular person. Like that, we will be coming up with inferences. You will be coming up with the model. So yeah, that's it for today, guys. I hope you have learned what exactly the linear regression is, how it is helpful for us to bring the inference, to build the model, and to predict the output. Here, what we are predicting. Here, what we are predicting, that's cost, how much premium each individual will have to pay. So what we have learned, what exactly the linear regression is, and when we will be going with linear regression, what is the difference between classification and regression, and what are the error matrix we'll be having, guys? RMSE, root mean square error, will be using more frequently, and we have other error matrix, error terms as well. Error terms, we are not using any of those. Presently, we'll be going with root mean square error. So yeah, this is all about the linear regression and how we can apply the linear regression into real life, and how can we do the prediction. So yeah, this is all for today, guys, and yeah, thank you for joining, and I hope you have liked this session. And if you want to see more of these use cases, in that case, keep following the 360DigiTMG, and in next session we will be coming up with one more use case and one more algorithm. We'll try to understand the algorithm first, and we'll try to apply it that algorithm using one use case scenario so that you can clearly understand how things work from end to end. Yeah, thank you for joining, guys, and have a nice day, and we'll see you in the next session.